anyway, we can so whole class into different subgroups, capture the CER variability, and put them into reduced transfer model and simulate the satellite observation. And then we can conduct MODIS-like retrievals using spatial computing and see how the retrieval cloud properties like COT and IWP are. And here is exactly the same MODIS collection 6 ice cloud model, and we consider different kind of uncertainties in our retrieval. So that's COT retrieval first. So panel, you have the x-axis means different profiles. You have homogeneous clouds in the middle, and you have severely profiles on the two sides. For this side, you have small particles near cloud. On this side, you have large particles near cloud top. So that for the arrow bar means retrieval uncertainty, and the different colors means different retrieval channels. So you can see that for COT retrieval, there's very impact from the ICVH impact. So you can see that the curve always flat. It is independent of ICVH. That's a totally different story. So here, when you have small particles near cloud top, you find that the retrieval underestimates the IWP by maybe 30% or even more. On this, you have larger particles near cloud top, the retrieval overestimates the overall IWP. That's a big surprise because the MODIS use shortwave channels, which are more sensitive to the upper parts of the clouds. That tells you this feature. So here, between the different retrievals using different channels, you find that the 37 micron, which is the yellow curve, gives the lowest on us. That's because channel ice crystals in that channel is the most absorptive one. Okay, now the question is how this impact could be for global monthly ice cloud records, for example, the MODIS level 3 products. To answer the question, we have to use realistic data from CALIPSO and CloudSat. We use year data from 2C ice and 2B geoprovider data, and then get the average CER profile from this data set. And you see those different profiles indicate clouds with different IWP. For very thin clouds, you have small IWP, and see profiles for those clouds, which is you have a little bit difference between the particles near top and near bottom. But when clouds goes thicker and thicker, you have complicated profiles. Eventually goes to this, the curve, which is very inhomogeneous. The particles increase very rapidly when you go deeper into the clouds. And we can use very simple linear regression to calculate the slope of the CER for each profiles, which is actually the black dots. In this plot, the y is CER profile slope as a function of IWP. So and then we can use a smooth curve to fit this plot. And we can get this relationship is very important. With this, we can estimate if we know the overall IWP, we estimate how the size distribute in the whole cloud layer. And then there's a relationship between the reference IWP with a retrieved IWP. To do this, we start from a randomly selected IWP and COT pair. And with the IWP, we can, with relationship, we just derived this equation. We can estimate the vertical distribution of CER. And then we them into reducer model and get the simulated observation, and then conduct MODIS-like temporal retrieval by assuming the cloud is homogeneous and get the retrieved IWP. And with this, so we can repeat the process again and again using different COT pairs and using different geometry. So, for example, this project we use 1.6 to this relationship. The axis reference unbiased IWP, and here is MODIS retrieved IWP. You can see that the MODIS is always underestimated in this side. That is true because according to the CALIPSO CloudSat observation, larger particles is always close to the cloud bottom. So that's consistent with our previous sensitivity study. And different colors here indicate different solar angle. Because that's when you have larger solar angle, the MODIS get larger bias for the 3 retrievals. So now relation, we can estimate how the unbiased IWP could be start from the MODIS product. So I share the MODIS IWP retrieved from 2.1 micron channel. Here are 2 different months, January and July in 2007. Here is the estimated unbiased IWP. So what we do here is just replace the MODIS IWP by the estimation, the unbiased IWP. We just replace this variable here. The difference is find that here's the MODIS minus estimation. You can see that this is the absolute difference. You can see that they are all negative, which means MODIS always underestimates the global ice water path. But there are some spatial structures here. For example, in January, in hemisphere, you have the bias here. That's because the solar density angle is larger in January in north hemisphere. Thing happened in southern hemisphere in July. That's also because of the solar density angle issue. And it has differences in terms of percentage. You can find that for average, the MODIS underestimates by about 30%. But for some local locations, for example, here, the bias can up to minus 50%. So which could have very large impact on global P on the level 3 data. Here the zoning of the MODIS retrieved IWP and estimation. So this is the straight curve, and the dash curve is the estimation. You can find that the estimation is always larger than the MODIS. Different colors indicate different signals. Here, one thing I want to emphasize is the 3 IWP is the lowest product. But here, let's assume that ICVH is the only reason for the ratio differences between the 3. However, if it is ICVH is not, then we should end up with almost identical retrievals after correction. But it is not. You can see that after correction, the reason is still the lowest part here. So that's ICVH is not the only reason for the retrieval difference between the 3. So one reason is that because the cloud phase detection, there are lots of maybe mixed phase clouds, or there are large fraction of clouds with maybe they have super cool liquid water on the cloud top, but below that there are all ice. To some cloud like that, so that can have a large impact on 3.7 retrieval. But that requires further investigation. Okay, fine. Let's look at the cloud radiation. So here, F1 shows the outgoing long wave radiation at TOA, and the right one shows the short wave. So you can see that here, the first row shows the radiation from the MODIS only, and the last shows the MODIS minus calculation using the homogeneous clouds by to consider the CER profiles. So you can see that although you find some spatial structures here, but if you look at magnitudes, they are very small. They are between negative and positive 0.5 watts per square meter, something like that. So you see that difference is quite small. So the IR have little impact on cloud radiation. So this is quite small in comparison to other uncertainties of clouds. For example, if you just simply replace cloud particle shape from one to another, for example, you change the shape from place to something others like column. That's very huge differences in terms. If you look at the flux, that can have maybe 20 watts per square meter or even larger. So this 5 watts per square meter, which is more very marginal. Okay, so for the summary for the first part, CVH could lead to relatively large IWP bias, but little impact on COT and flux biases. So you can see this this conclusion from this figure. So here you have gray bars here, which means the IWP bias. So the global average you have for MODIS, the underestimates global ice water pass by minus 35% for global ice cloud over ocean. But for thin clouds, the underestimation is not that strong, about 10%. When the cloud goes thicker and thicker, for very thick clouds, they have underestimation by minus 50%. And in terms of radiation, here the blue one is short wave, yellow is long wave, and the red one is the total. So for global average, the difference is less than 0.1 watts per square meter, which is very low. For very thick clouds, the difference is still very low, about less than 0.3 watts per square meter. I have a manuscript about this starting, and we have submitted to JGR, and we get some very positive feedback from reviewers. So hopefully it will march in next month, hopefully. Okay, so part 2. Uncertainty. So that's in the standard MODIS product, but I guess for IWP, because in MODIS they didn't retrieve IWP directly, they retrieve COT and the particle size, and the IWP is actually a product of that two variables. So it provides the for COT and uncertainty for particle size. So you combine them together, I think the typical for IWP could be about 50%. 50%, I have to say, but not quite. I'm not 100% sure about that. Mm-hmm. Yes, that's right. Good. Okay, part 2. So this part, this is actually a ongoing project. So which is using a joint observation from infrared and microwave sensors to retrieve ice water pass and the cloud top height. So as for individual instrument has its own limitations in information. It is sensitive to different parts of clouds. So if you stick with one instrument, it cannot cover the whole dynamic range of clouds. So the sense is combine them together. For example, use infrared sensors, it cannot handle very optically thick clouds. Microwave is not sensitive to very thin clouds. So if you get together, you overcome all of these shortcomings. Here's an example of how the combined retrieval works. So here's the uncertainty in terms of IWP as a function of cloud optical thickness. So if you use infrared only retrieval, which is the blue curve, you have more uncertainty if the cloud optical thickness is low. The uncertainty goes larger and larger when you have thicker clouds. And that's different. When you have small optical thickness, you have real uncertainties from microwave. But when the COT is larger, the microwave gives you uncertainty. So if you bind them together, which is a random, because of large information content you have, which gives you the lowest retrieval uncertainty. Advantage for the infrared and microwave is you have consistent daytime and nighttime evidence, so which is much better for investigative cloud diurnal cycle. Models have developed two models. One is for infrared and one is for microwave. For infrared, because I have enough time to go through details, the two papers describe the infrared model and the retrieval algorithm. So it is an optimization-based cloud retrieval algorithm. We retrieve cloud optical thickness and packet size, and also cloud tops using the MODIS infrared channels. And we have applied this method to the MODIS global data. And here you can see the comparison between the MODIS data product versus our retrieval. So they are very consistent. This is one of COT, and here's cutoff height. And for wave, Dong actually developed a microwave model for the microwave humidity sounder, MHS. So they found some relationship between the ice water path with the microwave, high frequency microwave observations. They have developed an empirical model for microwave channels, high 150 hertz and some sounding gigahertz channels. But we have to handle is, as I talked before, when you combine the infrared and microwave together, they have totally different spatial resolution. So for microwave, have, for example, the microwave is about 20 kilometers, but for they have 1 kilometer near their point of view. So this is an example of how the infrared observation change as a function of CE and COT. That there's this curvature here. So if you just simply average the infrared observation for the whole domain, you get a very huge nonlinear effect. So that can give you biased retrieval. So to handle this, so what we developed a so-called IWP-bin method. For this FOV, I should have n small pixels for infrared and a super large FOV for microwave. And here, the total number of observations we have for this. Infrared, we use 6 MODIS infrared channels, 8 to 14 microns. And for microwave, we use 2 ATMS high frequency channels, 165 and 183 gigahertz. So here's a total number of observations. For we conduct infrared only optimal estimation retrievals for each pixels. So here we use infrared observation only. So in this case, if we write the equations from infrared, we can retrieve cloud for each pixel. So IWP and cloud top heights for each pixel. This is step 1. And step 2, we can try to some strategies here group those subpixels. For example, here this is currently this is a strategies we are currently using. But in the future, we can find some better way to do this. Anyway, we group the small pixels by the infrared retrieved ice water path. For example, we can separate them into 7 different categories, smaller than 20 to 40 gram per square meter. So with this, we can separate the pixel groups, and then we can safely average the inferred observation for each group because we assume that each group, clouds in each group have similar cloud properties, so there's no non-linear effect there anymore. And updates the inferred retrieval with combined infrared plus microwave observations. So this we have average infrared brightness temperature for the 7 bins and times IR channels and the microwave observation for the whole domain. And we can write the closed equations like this. The first one is the infrared equation for each of the bins. And the one is microwave. The whole domain observation is actually when that is a combination of each part. So know the fraction of each part from infrared, so we can have this equation, and the total fraction is equal to 1. And with optimal estimation to retrieve cloud properties for each IWP-bin. So that's an example. Here I use ATMS footprint, for example. Here on the left side, this is the step 1. We use infrared retrieval for each pixels. You have this infrared only ice water pass. So after the update, we get this. So eventually we have a hybrid spatial resolution ice water pass retrieval. So that here shows the ice water pass distribution for different groups. So for if you have through 1, 2 through category 4, something like this, the gray one is the infrared only. The pink one is after the update. So for cloud pixels, very small ice water pass, but don't. So even if you have updates, there's no difference between the two. But when you have category 6 and category 7, ice water pass is large enough. The infrared started to trace. So it is the microwave dominant. So you can have a huge difference between before the updates. I'll show a case study for this. This is a MODIS granule over ocean, over open ocean. So most of this granule is covered by ice clouds. For example, here. There are very thick deep convection here in this region. Also some here. Maybe it's not clear for you. And this part they are liquid clouds. So we apply measure to this granule, and you can find that the difference between using different channels. Actually, we use microwave only retrieval. So this retrieval, you have retrieval near the deep convection center for this region. You have very nice retrieval. But for this, you have series. The microwave has no activity for those thin clouds. But if you use infrared only retrieval, this one is the infrared only. We use MODIS infrared channels. You see that for thin cirrus clouds in this region, it has performed quite well, but it starts to saturate around IWP close to 200 or 300 per square meter. And the one is the standard MODIS collection 6 retrieval. It has some good retrieval for thin clouds, but for deep convection, it still goes to saturate. Maybe it also could be caused by the vertical heterogeneity, as we talked before. But the thing is, if we use infrared plus microwave retrieval, which is this one, we have very nice retrieval for no matter kind of cloud it is. For working cirrus clouds in this region, it's close to the infrared only, but the convection is much better than this one, and it's to the microwave only. So very nice. And the pattern block comparison allows that CALIPSO check. So you can see that here the CloudSat track. We have different retrievals. The red one with uncertainty arrow bars is the combined retrieval, and the dark black line shows the CloudSat standard product, and the dark blue one is inferred only, and the light blue one is the MODIS standard product, and the yellow one, this one, is the microwave only. You can find that for very thick clouds in this region, the joint inferred plus microwave is very consistent with CloudSat, and but this region, you can see that the microwave only fails. They have low retrieval for this region, but the combined retrieval is very close to the inferred only and the MODIS. So which means the joint retrieval use combined inferred and the microwave can handle the very wide range of cloud dynamics. Okay, summary here. We have the joint inferred and microwave retrieval to retrieve clouds, optical ice clouds, water path, and the clouds top height. And we have the new method to handle the subpixel variability as I talked before. And at this time, we just write this method to collocate ATMS and MODIS instruments, but in the future we will change our inferred model to WIRS also. So once I have done that, we can apply this method to MPP, ATMS, and WIRS instruments. Yeah, I'll finish here. So I'm going to take any questions.
Chenxi. So how do you adjust the weight for the retrieval, the infrared and microwave?
Yeah, so the reason is if you look at here, so you can see the weight is actually the sensitivity of each model. So you have once you have very thick clouds, the infrared observation is starting to saturate. So there's no, if you calculate the Jacobian of the infrared observation as, for example, D brightness temperature, D cloud properties, it's almost zero. So when you put them in the optimal estimation, there's no sensitivity for infrared. So in that case, the wave is dominant. Yeah.
Then speaker again, and we ramp up. Thanks.